Okay, the lesson that I would like you to pay attention to in all these discussions is that if you have a positive charge inside that area, inside that closed surface, you just imagine this closed surface. It doesn't have to be a physical surface, you just imagine it. If you put a positive charge and then count the number of field lines passing through that surface with the understanding that if an electric field line goes from inside to outside, it's counted as plus. If an electric field line goes from outside to inside, should be counted as minus. If you just count the electric field lines passing through, let's say, this red area, it will be proportional to the charges inside. In this case, it is the plus Q charge. And in these sketches, we had fixed the convention that for every plus Q charge, I will draw 8 electric field lines. So here, this surface, there are 8 electric field lines passing through this area. And it doesn't change if I deform the surface. Similarly, here, if you consider this blue surface, there are no charges inside. Whatever electric field line enters that surface, it has to leave that surface. Because remember the properties of electric field lines. They can only start from positive charges or infinity and end in negative charges or infinity. So if there are no charges in this region, any electric field line that enters has to leave. Otherwise, it means it terminates somewhere. Or if there is an electric field line coming out, it means that it entered from somewhere else. So the contribution will, in any case, will be 0 because there are no charges inside. And hence, for whatever configuration you can imagine, if you evaluate the flux passing through a closed surface, okay, I also want to emphasize that one, it has to be a closed surface. The total flux passing through a closed surface is always proportional to the total charge inside. Because this total flux is the number of lines passing, is proportional to the number of lines passing through my surface, and that number of lines is all determined by the total charge inside. Now let's also determine that proportionality constant. Well, let's look at a simple case, which will give me that proportionality constant. Well, the simplest case we had studied was a point charge. We had already studied the electric field. The electric field lines are always radially out. Now let me evaluate this E dot dA integral over a closed surface. Well, I can pick up any closed surface that you like. But for simplicity, I will just assume a spherical surface. Let's just consider this sphere around that plus Q charge. Well, the electric field is always changing at every point. At least it's changing the direction on that surface. So again, we just divide it into very small regions. Let me imagine this very small area over here. First, we have to determine what is inside, what is outside. Well, I will just choose this to be inside. This is outside. So the dA vector should be pointing from inside to outside. So this is my dA vector. Now, dA vector is pointing radially outward. So that direction, I can show it by the r hat vector. Are you familiar with this r hat vector? It's the unit vector pointing radially outward from the origin at every point. At this point, it is this unit vector. At this point, it is this unit vector. At this point, it is this unit vector. Now, the electric field at this point is given by, what is the electric field? Well, K we had defined it at 4 pi epsilon, 1 over 4 pi epsilon 0. Then we have the Q over Well, it is a vector at the electric field. What is the direction of the electric field? Well, it is all, if you write it as q times r hat, that direction is always correct, independent of the charge of q, sign of q. Well, q dot r hat might be pointing in the r hat direction or in the opposite direction, depending on the side of q. Okay, so this is E. Let me also specify at the point R. This is the point R. Dot dA, this is 1 over 4 pi epsilon 0, q over r squared, r hat, well, this dA vector has a magnitude also, it's just the magnitude is dA. So this is the electric field. I have to take the scalar product with dA r hat. Well, it's just the product of the magnitude, product of these coefficients, then r hat scalar product with r hat, 1 over 4 pi epsilon 0, q over r squared, times dA r hat dot r hat. Well, what is the scalar product? Well, this is the r hat. It's not the r vector. It's just 1. Their magnitudes are 1, and the angle between them is 0. So 1 times cosine 0, which is also 1. This is 1. So E dot dA for that very small segment is 1 over 4 pi epsilon 0 times q over r squared times dA. Now let's calculate this one. We have to imagine covering our sphere by such very small areas and summing all over them. So that will give me this integral. This integral is equal to 1 over 4 pi epsilon 0 q over r squared times dA. Now let's see. As I go from one patch on the surface to the other patch, does this change? This is the same for all those very small patches, so I can just take it out of the integral or out of the summation. Q, as I go from one patch to the other patch, does Q change? It doesn't change. Or does it change as I go from one patch to the other patch? Yes or no? What is R? R is the distance of this patch from my charge. But remember, I assume the sphere. The definition of the sphere with the charge at the center. The definition of the sphere is that at every point, the distance of every point on the surface from the center is the same. So for this patch, R has the same value as this patch. You see, this R is just the length. It's not the direction. The radius vector changes from patch to patch. Its direction is different. But the magnitude of the radius vector is the same. It's the distance of the patch from the center. For a sphere, for every patch, that is the same. That is why R also doesn't change from patch to patch. So I can also take that out. This is 1 over 4 pi epsilon 0 q over r squared times the integral of dA. Now this dA is the area of one of the patches. And this integral just tells me that I am summing over all these patches. So I'm summing the areas of all the patches, making up my sphere. But that will give me the total area of the sphere. What is the area of the sphere? 4 pi r squared. There's no 3. The area is just 4 pi r squared. But you see, there's a 4 pi over here, which cancels the 4 pi from this integral. There is a 1 over r squared here, which will cancel the r squared from that integral. This 4 pi's should cancel. R squares will cancel. So E dot dA is equal to Q over epsilon 0. Now note also that although we are fixing our shape to be sphere, the radius of the sphere was arbitrary. And our previous discussion basically told us that independent of which shape you take, that integral should not change. Now here, the shape was a sphere, but the radius was arbitrary. But still, the result is independent of the radius. If you imagine a larger sphere, on the surface of a larger sphere, the electric field will be smaller, but the area will be larger, and those two effects, they just compensate for each other. So the value of the integral just doesn't change as you change the size of your area, size of your sphere. And in fact, we had already said before that this integral, whatever shape you use, its value is independent of the surface you choose, as long as you are not changing the number of charges inside. Now, if you have a more complicated charge distribution, some of them are plus Q charges, some of them minus 2Q. Well, let's just put them arbitrary. This is Q1, Q2, Q3, up to Qi. Let's just imagine an arbitrary surface this time. Just imagine our arbitrary surface, as complicated as you like. Now, if you want to calculate E dot dA, first you should calculate the electric field. Well, the electric field created by all these charges at a given point on, let's say, on the surface P, at some arbitrary surface on point on the surface, let's say R, this will be equal to, well, we know that the electric field has a superposition principle, so the total electric field created is the sum of the electric fields created by each one of the charges. So this is the sum of EI. EI is the electric field created by the charge Qi. So E dot dA over a closed surface will be equal to sum of the integral of EI dot dA over the same surface. But we had just shown that that integral, although here in this case we had shown it for a sphere, our previous arguments show that this integral is independent of the surface. So also for this surface, so that integral dot dA should be equal to Qi over epsilon 0 if Qi is inside the surface well, if the charge is outside the surface, as in the example, the blue surface over here or the green surface over here, if the surface is outside, the integral is just 0. So at this integral, the integral of the electric field created by the charge Qi over this arbitrary surface we chose, it is either Qi over epsilon 0, if the charge is inside. For this charge, for example, it will be Qi over epsilon 0. But for this charge over here, it will be just 0. So let's look at over here. These integrals, depending on whether Qi is inside my surface or outside, will be either the charge or 0. Only the charges inside gives me a non-zero integral. So the sum will be only over the charges inside. So E dot dA will be equal to sum over Qi over epsilon 0 for Qi inside the surface. Here I am summing over Qi over epsilon 0, but only if Qi is inside my surface. Here I have a summation over all the electric fields created by all the charges, whether they are inside or outside. But when I take this integral, only the charges inside contribute. The charges outside do not contribute to my integral. And I would like to repeat here that although the charges outside the integral do not contribute to this integral, the charges outside the surface, they do contribute to the total electric field. So if there are charges outside, it will change the electric field, but it will not contribute to this integral. So this E dot dA integral for an arbitrary charge distribution, arbitrary shape, is always equal to the Q enclosed divided by epsilon 0. This is what is called the Gauss's law. So if you calculate the total flux passing through a surface, then it is always equal to the passing through a closed surface, it is always equal to the total charge enclosed by the surface divided by epsilon 0. If there are no charges inside, if Q enclosed is 0, then this integral is 0. But that doesn't mean that E should be 0, by the way. Now we will do some applications of this. Any questions? Well, you see, okay, let me also, okay, we had two steps in our proof. The first step was to prove that whatever the shape is, the value of this integral does not change. Whatever the shape, for every shape, this integral is always equal to the total charge, proportional to the total charge inside. Then the question was, what is this proportionality constant? It should be a constant. You see, the right-hand side is independent of the shape. So it should be a constant, independent of the shape also. So I chose a particular shape, a special shape, to determine that constant. But that constant, since it's independent of the shape, it should be the same for every shape. This is one reasoning. Now, another reasoning you can have now let me look at an arbitrary shape. This is my plus Q charge. And then let me imagine a sphere inside. I have this arbitrary shape, there is a sphere inside. Now let me look at a patch outside. Let me call it da prime. Well, if I just connect all the edges to my charge, there will be an analogous shape over here, a smaller one. Now on this shape, the electric field will be small, the area will be large. On this shape, the electric field will be larger, but the area will be smaller. How large will the electric field be here? Well, it depends on this distance. If this distance is twice this distance, then the electric field here is 4 times larger than the electric field over there. But similarly, the area over here it will be 4 times smaller. So the contribution from this area and from this area will be the same. So for every area outside, I can match it to an area on this sphere, as long as there are no charges inside. So this is another proof. Well, it's kind of more complicated, but I would rather stick with this counting of the electric field lines. The number of lines is independent of which shape you use. And to fix a constant, since it's the same, it should be the same constant for every shape, you can choose a simple surface. Now, in fact, this Gauss's law, although we had derived it in electrostatics, it turns out that it is valid also in electrodynamics. Even if the charges are moving around, even if they are accelerating, etc., no matter what the charges are doing, that law is still valid. Let's do the applications. The easiest one would be the electric field of a point charge. You see, we already used the electric field of a point charge to derive the Gauss's law. But we can also go it the other way around. If we knew the Gauss law, we can just calculate the electric field of a point charge. In that sense, they are equivalent. Now, the Gauss law is always valid, whatever the charge distribution is. But that doesn't mean that it is always useful. So we cannot use it to solve for the electric field for an arbitrary charge distribution. But for certain special cases, it is quite a powerful method. But the reason for this is, before using the Gauss law to be able to calculate the electric field, we still need to know something about the electric field itself before knowing its magnitude and magnitude. For example, if you have a point charge, let's imagine this one. Instead of looking at it like this, if I rotate my system around my charge, does my charge distribution change? Well, if the charge distribution does not change, if I just rotate my system, then so does the electric field should not change. So anything, any transformation, let's say, that doesn't change my charge distribution should also leave my electric fields invariant. My electric field also shouldn't change. One thing is, if I rotate my electric charge, system around this point, the electric field should not change. Now that already tells me one thing. If you are used to using spherical coordinates, r, theta, and phi, well, if I'm rotating my system, I'm essentially changing theta and phi coordinates of a point. Do you agree? Well, that means that if I change the theta and phi values of the electric field, my electric field should not change. So what I'm meaning is the magnitude of the electric field, at least. In principle, it can depend on all of these coordinates. But since if I rotate for arbitrary rotations around this point, the magnitude should not change. But that tells me that the electric field is a function of R only. It cannot depend on anything else. Do you agree? Well, let's imagine the contrary. Let's say that the magnitude of the electric field depended on theta and phi. What would that mean? For example, for this point, I will have a weak electric field. But for this point, at the same distance, I will have a stronger electric field. If this would happen, well, I rotate my system and everything changes in my system, meaning that the electric fields change. The charge distribution doesn't change, but the electric fields change. That shouldn't happen. That is why the electric field only depends on R. Now, secondly, what about the direction of the electric field? What can I say about the direction? Let's assume the electric field here is pointing in this direction. Then the electric field here, well, maybe it points in that direction. Is it possible? Okay, if I'm asking, it's not possible, but why? Well, let's imagine rotating my system. Well, if I rotate my system by 90 degrees, the charge distribution will not change. Well, the charge is still a point charge, but now this vector will rotate to that vector. So at the top, this will be the electric field, and that point will move over here. I'm rotating everything, so the electric field will be pointing in that direction. You see, universe doesn't really care how do we stand and look at it. So you can look at that charge distribution like this, or rotate your head by 90 degrees and look at the same system. Well, then you would say that if this were the case, the electric field of a point charge should be this one and this one. But that cannot be. So you see, although the charge distribution doesn't change, when you look at it like this or rotate your head by 90 degrees and look at it, the charge distribution doesn't change, the electric fields change. That cannot happen. If the charge distribution doesn't change when you change your orientation, the electric field should also not change when you change your orientation. So the electric field lines also cannot have that shape. So this is also not possible. Now I'm looking for a direction of electric field lines which will not change as I rotate my head. Any proposals? Okay, so let's see. Can it do this? This is a plus Q charge. They all start from positive and go to infinity. Is this possible? Well, let's see. We said that, okay, let's look at it like this and rotate our head 90 degrees and let's look at it again. Does it change? It doesn't change. It's the same. Okay, so at least this is what we call rotating your head or rotating your system, what we call rotational symmetry. The charge distribution has rotational symmetry, and because of that rotational symmetry, the electric, if we just use the rotational symmetry, this is also possible. But there's another symmetry. Let's imagine I put a mirror over here, just passing through my charge. Does my charge distribution look different if I look through the mirror? My charge distribution. So let's just imagine a mirror. You are going to the world of Alice through the mirror. Well, my charge is still, I have a point charge over there also looking through the mirror. The charge distribution still doesn't change if I look my system through the mirror. But my electric field lines will look different. Instead of swirling it in this sense, through the mirror, they will just swirl on the opposite side, sense. So again, although my charge distribution doesn't change when I look through the mirror, if the electric field lines did this swirl motion, then through the mirror they will look different. But if I have the same charge distribution, I should have the same electric field lines. This is also not possible. In fact, the only possibility is if the electric field lines is radially outward. So if I have a positive charge, the electric field lines have to be radially outward. One reason, as your friend pointed out, the electric field lines have to start from the positive charges. And they cannot make swirls, they cannot circle around, because then through the mirror it will look different. But if you have this radially outward system, if you look at through the mirror, it will basically look the same. Just imagine a mirror. Well, this will look like this. This will look like this, etc. So the mirror, the image through the mirror will be exactly the same. Are you following? So hence, through the mirror, the charge distribution does not change. And if the electric field lines are pointing radially outward, the electric field lines also, the electric field lines also do not change, which should be true. Okay, so what do we know about the electric field lines of a point charge without using any Gauss's law, just using these symmetry arguments? For a point charge, the electric field has to be, the magnitude can only depend on the radial distance. It cannot depend on the angles. As long as I'm here or here or here, as long as my distance doesn't change, the electric field magnitude cannot change. Its direction changes, but it should always be radially outward. So this much I already know about the electric field, just using what we call the symmetry argument. Now we have to evaluate this integral. You see, the problem is if you want to evaluate an integral, you have to know the function that you are integrating. But here, the thing is, I don't know the electric field. I cannot really integrate it without knowing the electric field. But the point here is to be able to obtain the electric field. But you see, if you are integrating a function that you do not know, if there are certain constants, you can just take them out of the integral. And what remains, you might be able to integrate. We already know the electric field. Okay, the direction is constantly changing, but the magnitude might be constant on certain special surfaces. So what is the surface over which the magnitude of the electric field does not change? A sphere. So over a sphere, the magnitude of the electric field, although it is unknown, it is constant, I can just take it out of the integral. And hence, I might be able to evaluate the remaining integral. So this should be always equal to Q over epsilon 0. And now you said that the magnitude is constant over a sphere. Let's just consider that sphere. You see, this is true for every surface. Whether it's a sphere or a cylinder or a cube, for every surface, this result is correct. Not much useful, but correct. Now let's apply this result to a sphere around my charge Q. Let's take this sphere. That's a sphere with charge Q at the center. Well, at every point, I can imagine an area, a very small area vector. And that area vector, its magnitude will be the magnitude of that very small area, and its distance, its direction will be in the radial direction. Now I have chosen my surface based on my knowledge of the electric field. I know that the electric field is in the radial direction. The area vector is in the radial direction. Now I can go and evaluate this integral for my sphere. Let's say that the radius of the sphere is capital R. E dot dA on the surface of my sphere will be the magnitude of the electric field. At every point on the sphere, the radial distance is just capital R. So electric field magnitude at a distance capital R times R hat, scalar product with the dA vector. So this is my electric field. This is the dA vector. If I take their scalar product, A dot dA just becomes ER times the area. Now I can put this back into my integral expression, my Gauss law. So Q over epsilon 0 should be equal to ER times dA. Now, as I promised, this is just a constant over my surface. So I can take that constant out of my integral. If I take that out of my integral, what remains is, this is the area of one of the patches making my sphere. I just sum over all the patches. That gives me the total area. And that total area is the total area of the sphere, 4 pi r squared. So Q over epsilon 0, electric magnitude of the electric field at a radial distance r times 4 pi r squared, or the magnitude of the electric field is Q over 4 pi r squared epsilon 0. But now we know the electric field. You see, we already know that the electric field at the position given by the r vector, this will be just this ER evaluated at that distance. This is equal to 1 over 4 pi epsilon 0 Q over R squared. And the electric field, we started by showing that it's in the radial direction. So basically, starting from the Gauss's law, we could derive the Coulomb law for point charges. That R squared is coming from the surface area. So for example, in the beginning we had also said, why do we have the gravitational force and the electromagnetic force? Both of them have the 1 over R squared behavior. Because basically they both satisfy the Gauss's law, and the 1 over R squared is essentially the surface area of a sphere in 3 dimensions. Since we are living in a 3-dimensional space, the forces are, all the forces we know, they have this 1 over R squared behavior. Any questions? So if we go over the steps that we use to derive this, so first of all, Gauss's law is valid for every charge distribution and for every surface that you can imagine. It's always true. Now, if you want to apply it to a particular problem and to be able to use it to calculate the electric field, you first have to study the properties of the electric field. What can you say about the electric field? Now, in this particular problems, we first determined, without using the Gauss's law, we first said that, okay, the point is very symmetrical. If you rotate it around itself, it doesn't change. If you put a mirror passing through that point, it doesn't change. Since the charge distribution does not change, the electric field it creates also should not change. And then using this argument, we first show that the electric field at a given point its magnitude has to depend only on the distance from my charge, and its direction has to be radially outward. So that is the first thing we have determined. Now, once we know these properties, that it is always radially outward, and the magnitude only depends on the radial distance, then we ask us the question, okay, over which surface can we evaluate this integral, although we don't know what this function is? In general, if you want to evaluate an integral, you have to know the function that you are integrating. But here we don't know. But nevertheless, we chose a surface over which, in this case, R was constant, which was a sphere. On the sphere, this is just a constant. So this Q over epsilon, which should be equal to E dot dA, that on the sphere we wrote it as the product of the magnitudes. And then we said, okay, fine. So this is a constant. So we took it out of the integral. And what remains inside the integral, we could evaluate explicitly. So that will be the trick also in other applications. First, we have to analyze the electric field itself. What are its properties? And from that knowledge, we have to determine a surface over which the unknowns in the electric field are either constant or the contribution from that region should be 0. That's also another possibility. We will see some examples of that. So we could take out the constants out of the integrals. We evaluated what is remaining, and that allowed us, by putting it back in the Gauss's law, that allows us to determine the unknown functions. And hence, once we determine the unknown functions, we know the electric field. That will be the step for every application of the Gauss's law. first identify the properties of the electric field, not necessarily the magnitude, but general properties. Determine a surface over which the electric field magnitude is a constant. Use that surface to evaluate the integral in the Gauss law and determine the unknown constants. Okay, any questions? See you on Monday.